Hello class, welcome to SciChem. Here we are another session for lecture number 3 of phase equilibrium. So in the previous class we have already discussed about what is phase and component, and we have discussed how to calculate phase in a system and how to calculate component in a. Now we are going to discuss about degree of freedom. Degree of freedom. So what is degree of freedom? It may be defined as minimum number of independent factor or variable to define term. So it may be defined as the minimum number of independent factor or variables or independent variables to define a system completely. In thermodynamics, we can define a system. Let us consider, here we are, water is present in a liquid state. So in order to define a system, the variables are pressure, temperature, number of moles, etc. So in order to define a system, what is the minimum number of variables I need? The minimum number of variables to define a system, that is water, liquid, I can put here minimum number of variables equal to minimum number of variable equal to 2, that is pressure and temperature. Why minimum number of variables is equal to 2? That means if I put pressure constant, that is 1 atm, by putting pressure 1 atm constant, temperature is independent of that pressure, which I mean to say that if I put pressure 1 atm, that is constant, temperature is independent of that pressure, means the water can exist at 1 atm pressure, that is constant, in liquid state at 25 degrees Celsius, at 35 degrees Celsius, at 45 degrees Celsius, at 65 degrees Celsius, at 1 atm pressure if I put constant. So here temperature is independent of the pressure. So we need two minimum variable, that is pressure and temperature, to define this H2O liquid system. If we consider another system, let us consider it is closed vessel, closed system. Here water, liquid is in equilibrium with water gas. Water liquid is in equilibrium with water gas. That means H2O liquid is in equilibrium with H2O, and it is in equilibrium condition, and this equilibrium condition have pressure 1 atm and temperature is 100 degrees Celsius. Here pressure and temperature are dependent on each other. That is, if I put pressure 1 atm constant, then temperature, if I put pressure 1 atm as a constant and I will change the temperature, that is 95 degrees Celsius or 105 degrees Celsius, the phase changes, because this equilibrium is achieved at a particular temperature and a particular pressure. If I by putting pressure constant and changing temperature, the phase will changes. Here one point you need to note, remember number of phase should not change by changing variable. This is important. Number of phases should not change by changing variable. Again, I am considering first case. One water liquid is present. If pressure 1 atm is constant, then the water is in liquid state at 25 degrees Celsius, 35 degrees Celsius, 45 degrees and 65 degrees Celsius. So here the minimum number of variables required, that will be 2, that is pressure and temperature. But in this condition, since equilibrium is attained, if I put pressure 1 atm constant and by changing temperature, the phases changes. Either we will find complete gas or complete liquid by changing temperature. That means phase changes. So number of phases should not change by changing variable. It is important. So here temperature and pressure are dependent on each other. Temperature and pressure are dependent on each other. So here degree of freedom is 1, which is called monovariant. Here temperature and pressure are independent of each other. Independent of each other. So degree of freedom DOF is equal to 2, is called divariant. Here monovariant. Again I am considering another equilibrium, water solid in equilibrium with water liquid, water, and this equilibrium is attained temperature 0.0075 degrees Celsius, 4.5 mm of mercury, and this temperature is called triple point. Here temperature and pressure is always fixed. That means if I change any temperature or pressure, then the equilibrium will be affected. Equilibrium will be. So here I can say that for this equilibrium condition, degree of freedom equal to 0, which is generally called non-variant or invariant. So what is degree of freedom? It is the minimum number of independent factor or variable that should be required to define a system completely. So first case we have taken only liquid water. In second case we have taken the equilibrium between liquid and gas. In third case we have taken the equilibrium between water solid, water liquid and water gas. Here since temperature and pressure is fixed, at this temperature and pressure only this equilibrium between three states or three phases are achieved. By changing any temperature, the phases changes. Number of phases changes. So I can simply say that is mono as temperature and phase fixed. Mono condition should be satisfied for current phase be and in So what are the conditions that should be satisfied for different phases to present in equilibrium? That is phase equilibrium. In phase equilibrium, what are the conditions for the phase to be present in equilibrium? Here three conditions. One condition is thermal equilibrium. Thermal equilibrium. Thermal equilibrium means all phase should be in same temperature. This is called thermal. All the phases which are in same temperature are called thermal equilibrium. Simple, I am giving the example. In this equilibrium, it is phase 1, it is phase 2. Here 100 degrees Celsius, it is also 3. These are in thermal equilibrium. Another equilibrium is mechanical equilibrium. That means all phases should have same pressure. So mechanical equilibrium means all phases should have same pressure. Another is chemical equilibrium. Chemical equilibrium means we need to know chemical potential denoted by mu. It is free energy change per mole. It is defined as free energy change per mole. That means why chemical potential is important? Chemical potential is important due to which phase in which temperature and which pressure is stable can be known by chemical potential. That is, at which temperature and which pressure which phase is stable can be known by chemical potential. That means chemical potential is also called escaping tendency, which we have already studied in thermodynamics. So for a chemical equilibrium, let us consider phase A is in equilibrium with phase B in equilibrium with phase C, and A component is present in phase A component is present also in phase B, A component is present also in phase C. So in order to satisfy chemical equilibrium, that is chemical potential of a component A in phase A. Chemical potential of a component A in phase A should be equal to chemical potential of a component A in phase B should be equal to chemical potential of a component A, and this is the condition for chemical equilibrium. Again, this is chemical potential of a component A in phase A. chemical potential of component A in phase B, chemical potential of component A in phase C should be equal. Then at that condition there will be chemical equilibrium. So for phase equilibrium we need to satisfy the phases should satisfy three types of equilibrium: thermal equilibrium, all phase should be in same temperature; mechanical equilibrium, all phase should have same pressure; chemical equilibrium, chemical equilibrium can be determined by chemical potential. Chemical potential is the change in free energy change per mole. So the component A, the chemical potential of component A in phase A, chemical potential of component A in phase B, and chemical potential of component A in phase C, all should be equal. Then there will be chemical equilibrium. So after this we are going to derive Gibbs phase rule, that is degree of freedom is equal to number of components minus phase plus 2. For this derivation, so what is the importance of Gibbs phase rule? It describes mathematically relationship between the relationship for determining the stability of phase present in material equilibrium. So it describes mathematically relationship for determining the stability of phases present in material equilibrium condition. Material equilibrium condition means thermal equilibrium, another is chemical equilibrium, another is our mechanical equilibrium. So let us consider we have a system in which two components are present, that means A plus B solution, and A plus B solution above B here the vapors of A and B are. In order to define this system, I need variables, that is temperature one variable, pressure another value, and another variable is composition of a component in phase 1, that is liquid, and phase 2, that is gas, which I mean to say that if component A is represented by Ca and component B is represented by Cb, what is the composition, or I can simply write mole fraction of A in phase 1 and mole fraction of A in phase 2, and what is the composition of mole fraction of B in phase 1 and mole fraction B in phase 2. Age A plus B is present in solution, that is liquid phase. A plus B is also present in vapor phase. So this is component 1 and component 2 AB. So I need to define what are the composition or concentration composition of substance component A in one phase and component B in another phase. So I need this 4 variables plus P plus. So in order to define this system, I need variables, that is 6 variables, 4 variables composition variables and another 2 variable, that is T and P. Similarly, if we consider a system which contains P phases and C components. Here 2 components are present, but here I am telling C components are present. If a system contains P phases and C components, P phases and C components, then the concentration or composition variable will be P into C. Then the composition variable will be P into C. That is, here again, why P into C? Here phase is 2, component is 2. So composition variable will be 2 into 2, that will be equal to 4. 1, 2, 3, 4. So if there are P phases and C component, then concentration or composition variable will be P into C. And we have since there is P phases and C components, another temperature is one variable, pressure is another variable. So concentration composition variable, total variable will be equal to Pc, this is concentration composition variable, plus 2. Why 2? 2 is for temperature and pressure. So total variable will be Pc plus 2. But this Pc plus 2, but all the Pc plus 2 variables, but all the Pc plus 2 variable are not essentially independent variable because of restricted condition. Since there are many P phases, there should be restricted condition, and we have to calculate what are the restricted condition or what are the equations we need to calculate. So first, the restricted imposed in phase equilibriums are the restriction imposed phase equilibrium are, the restriction imposed in phase equilibrium are the sum of mole fraction the sum of mole fraction of all component in a phase is unity. Sum of mole fraction of all component in a phase is unity. That means if we have two component A and B, that is mole fraction of XA plus mole fraction of XB, that should be equal to unity. Since we have P phases, that means sum of mole fraction of all components in a phase is unity. So I am writing for phase 1 mole fraction of component 1 in phase 1. Again, what is the meaning of this? Let the system contains 1 2 3 dot dot C component and have phases 1 2 3 dot 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 P phases. This is mole fraction, this is component 1 and this is phase 1. So this is mole fraction of component 1 in phase 1 plus mole fraction of component 2 in phase 1, mole fraction of component 3 in phase 1 dot 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 mole fraction of component C in phase P should be equal to. Similarly, if I am considering phase 2, so I am writing here mole fraction of component 1 in phase 2 plus mole fraction of component 2 in phase 2 plus mole fraction of component 3 in phase 3 plus dot dot mole fraction of component C in phase P equal to 1. So if I have P phases, then I can get P equation. If I have one phase, I get one equation. For two phase, second phase, two equation. If I have P phase, then I can easily get P equations. And another is for chemical equilibrium. We have already studied, that is component 1 in phase 1 should be equal to, this is chemical potential of component 1 in phase 1 should be equal to chemical potential of component 1 in phase 2 should be equal to chemical potential of component 1 in phase 3. For this is for phase 1. If I am considering phase 2, then also same, chemical potential of a component 2 in phase 1 should be equal to chemical potential of a component 2 in phase 2 equal to chemical potential of component 2 in phase 3 should be same, so that they can achieve chemical since we have p phases, there will be p minus 1. How p minus 1 equation? That means if A is in equilibrium with B, B is in equilibrium with C, we need two equations. That means this is phase 1, 2, 3. When there is 3 phase, we need 2 equations. So for p phases, we need p minus 1 equation. And we have C component. So we need C into p minus 1 . This is our equation 1. This is our equation. From these above two cases, I can say that total equation, that is p plus c into p minus 1. So now we are going to calculate degree of freedom, that will be equal to number of variable that should be specified minus number of equation